You are stardust. Have you ever wondered where the elements in your body came from? The carbon in your cells, the calcium in your bones, the oxygen you breathe, none of it was created on Earth. Every atom that makes you, was forged in the heart of a star. As Carl Sagan once said, we are made of star stuff. But how exactly does the universe build the periodic table? Today, we embark on a journey across cosmic time, from the Big Bang to the fiery deaths of stars, to uncover how the universe created the chemical elements and ultimately, how it created us. Imagine the periodic table as a layered timeline of cosmic events. Hydrogen and helium, born minutes after the Big Bang. Carbon and oxygen, cooked slowly in the furnaces of ancient stars. Gold and uranium, forged in violent stellar deaths and catastrophic neutron star mergers. NASA, ESA, and CERN have all developed periodic tables showing the origin of each element. These visualizations reveal how complex the story really is and how interconnected we are with stars that lived and died billions of years ago. We'll explore all of these processes, breaking them down into three major categories. Big Bang Nucleosynthesis, when the universe first cooled enough to form matter. Stellar nucleosynthesis, the steady fusion reactions inside stars. Explosive and exotic nucleosynthesis, the violent events that create the heaviest elements. But first, let's begin at the very beginning. Big Bang nucleosynthesis roughly 13.8 billion years ago. The universe was born in an event we call the Big Bang. But in its first moments, there were no atoms, only a chaotic sea of subatomic particles, quarks, gluons, photons, neutrinos, and leptons. As the universe expanded, it cooled, and within the first second, quarks combined to form protons and neutrons. Then came a brief but critical period known as Big Bang Nucleosynthesis (BBN), lasting from about 10 seconds to 20 minutes after the Big Bang. This was the universe's first attempt to assemble the elements. In this tiny window of time, the extreme temperature over 1 billion Kelvin and high density allowed fusion reactions to occur, similar to those inside modern stars, but on a cosmic scale. Here's what the universe managed to produce. Approximately 75% hydrogen 1A, single protons, 25% helium for He, stable and abundant, trace amounts of deuterium H, heavy hydrogen, helium 3 cubed He, lithium 7 Sli. This composition has been confirmed by cosmic microwave background (CMB) measurements and by studying ancient gas clouds, as predicted by the standard Big Bang model. Despite the energy, the Big Bang did not produce anything heavier than lithium in significant amounts. Why? Temperature dropped too quickly. Fusion is time-sensitive. The universe expanded and cooled at a rate that cut the fusion window short, leaving no time to build heavier nuclei. There are no stable elements with atomic number 5 or 8. This is known as the mass gap, an obstacle in nucleosynthesis. For example, beryllium-8 is unstable and decays almost instantly. No stable element exists with 5 protons equals 5. This created a bottleneck. Fusion couldn't easily progress beyond helium. Astrophysicist Steven Weinberg, in his book The First 3 Minutes, described this as a universe with just enough time to make helium, but not enough to go further. Although BBN produced only a handful of elements, this stage laid the foundation for everything else. It set the initial chemical composition of the cosmos, gave rise to the hydrogen and helium that would later fuel stars, allowed the formation of neutral atoms after 380,000 years, enabling the release of the cosmic microwave background radiation we observe today. Even today, BBN remains one of the cornerstones of modern cosmology, providing strong evidence for the Big Bang and helping constrain parameters like the baryon-to-photon ratio and the number of light neutrino species. Stellar nucleosynthesis begins after the Big Bang. The universe entered a long period known as the Cosmic Dark Ages. There were no stars, no galaxies, only vast clouds of hydrogen and helium drifting through space. It wasn't until a few 100 million years later that gravity began to pull these gases together, forming the first stars, known as population 3 stars. These stars were massive, hot, and short-lived. They contained virtually no metals in astronomy. Metals equals any element heavier than helium, making them chemically pristine. Population 3 stars were likely hundreds of times more massive than our Sun, and they burned through their fuel quickly, setting off the first waves of nucleosynthesis since the Big Bang. At the heart of every star is a nuclear fusion reactor. When a star reaches sufficient core temperature, approximately 10 K in pressure, hydrogen nuclei protons begin to collide and fuse into helium, releasing vast amounts of energy in the form of gamma rays. Two primary pathways exist for hydrogen fusion, depending on stellar mass. 1. Proton-proton, pp chain dominant in low-mass stars like our Sun. Converts for protons hydrogen nuclei into one helium nucleus, releases positrons, neutrinos, and gamma radiation. This process was first detailed in the 1930s by Hans Bethe, who later received the Nobel Prize in 1967 for his work to cycle carbon, nitrogen, oxygen. Dominant in high-mass stars T greater than 1.5 times 10 K. Uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. The CNO cycle was theorized by Bethe and Carl von Weizsäcker, and its dominance in hot, massive stars was later confirmed by stellar spectroscopy. The energy from fusion exerts outward pressure, countering gravity, a balance known as hydrostatic equilibrium. This balance defines the star's structure, stability, and longevity. Small stars burn slowly, lasting billions of years. Massive stars burn quickly and die young, in just a few million years. As hydrogen runs out in the core, stars must fuse heavier elements to survive. This leads to the next stage of nucleosynthesis, the fusion of helium and beyond, which we'll explore next. From helium to iron, the end of fusion when hydrogen in a star's core is exhausted. Fusion halts, and gravity takes over once again. The core contracts and heats up, reaching approximately 10 K, enough to ignite a new kind of reaction, helium fusion, also known as the triple alpha process. In this reaction, the helium nuclei alpha particles fuse to form beryllium-8, Be, unstable and fleeting. If a third helium nucleus collides with Be quickly enough, it forms carbon-12C. This delicate two-step process was first explained in the 1950s by Fred Hoyle, who even predicted a resonance energy level in carbon to allow this reaction, a prediction confirmed by experiment, and often cited as an example of anthropic reasoning. Carbon-based life depends on this precise nuclear state. In stars with at least 8 to 10 solar masses, the core temperature becomes high enough to sustain further fusion reactions. Carbon fusion, approximately 610 K gives neon, sodium. Magnesium neon fusion, approximately 1.2 times 10 EK gives oxygen, and magnesium oxygen fusion, approximately 1.5 times 10 EK gives silicon. Sulfur, phosphorus silicon fusion, to 0.7 times 10 EK gives nickel 56 Ni, which decays into iron 56 Fe. These reactions happen in concentric shells, like layers of an onion, each fusing different elements. This was confirmed through stellar modeling in the 1970s and later through supernova spectroscopy, where elements like silicon, calcium, and iron are observed in the outer layers of exploding stars. Fusion up to iron 56 is exothermic. It releases energy that supports the star. But fusing iron or heavier elements is endothermic. It consumes energy instead of producing it. Why? Because iron has the most tightly bound nucleus of any element. This means you can't extract more binding energy from fusing it. Trying to fuse iron drains energy from the core. As a result, once iron accumulates in the core, no more energy is produced. Hydrostatic equilibrium collapses. Gravity wins. The star is now living on borrowed time. When the iron core grows to around 1 point for solar masses, the Chandrasekhar limit, electron degeneracy pressure fails. The core collapses in less than a second, reaching speeds of up to 70,000 kilometers per second. This triggers neutronization. Electrons and protons combine to form neutrons and neutrinos, a sudden bounce and shockwave, creating a core collapse supernova, the final and most spectacular stage in a massive star's life. This event not only marks the death of the star, but the beginning of the most exotic form of nucleosynthesis, where elements heavier than iron are born. That's what we'll explore next. Supernovae and the forge of heavy elements when a massive star reaches the end of its life. And as iron core collapses, a core collapse supernova is triggered. This is one of the most energetic events in the universe. In a matter of seconds, the star releases more energy than our sun will emit in its entire lifetime. The shockwave generated by the collapsing core, combined with an intense outflow of neutrinos, over 10 of them, creates conditions of extreme temperature greater than 10 K in neutron density. These conditions are perfect for building the elements that ordinary stellar fusion cannot. Elements heavier than iron. The primary mechanism for creating these heavy elements is called the rapid neutron capture process, or our process. Here's how it works. Nuclei are bombarded by neutrons at such a high rate that they rapidly absorb them before beta decay can occur. Once the neutron flux subsides, these neutron-rich nuclei undergo beta decay, converting neutrons to protons and stepping up the periodic table. This process produces many of the universe's rarest and heaviest elements, including gold, platinum, PT, uranium, thorium, TH. The Are process was first proposed in the 1950s by Hans Swiss and Harold Urey, and later refined by Alastair Cameron and George Wallerstein, who modeled nucleosynthesis pathways in supernovae. The evidence for supernova nucleosynthesis comes from multiple sources. Spectroscopic analysis of supernova remnants, e.g. Cassiopeia A, shows emission lines from elements like iron, nickel, cobalt, and strontium. Isotope ratios in meteorites contain radioactive remnants of short-lived nuclides like aluminum-26 and iodine-129, which must have been formed in nearby stellar explosions. The solar abundance curve, a plot showing how much of each element exists in the solar system, matches models of our process production in supernovae. In a landmark 2003 study published in Nature, astrophysicist Stan Woosley demonstrated through simulations that type the supernovae could produce nearly all elements from iron to uranium under the right conditions. Neutrinos don't just pass through matter in supernovae. They shape the nucleosynthesis environment during core collapse. An enormous burst of neutrinos interacts with matter, affecting the neutron-to-proton ratio. This balance determines whether our process can proceed efficiently, which isotopes dominate the final element yields. Recent models by George Fuller and Shunsaku Horiuchi, UC San Diego, 2018 highlight how neutrino flavor oscillations, where one type of neutrino transforms into another, could even affect which elements are created in different regions of the supernova envelope. Although supernovae can explain the origin of many heavy elements, researchers began to notice inconsistencies in abundance patterns, especially for elements like gold and platinum. Could there be another, even more extreme environment for our process nucleosynthesis? Yes, and it wasn't discovered until 2017, a moment we'll explore in the next part. Neutron star mergers and the gold in your ring. On August 17, 2017, the universe whispered in gravitational waves, and humanity listened. For the first time ever, scientists at LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event named GW170817. Just 1.7 seconds later, telescopes around the world picked up an electromagnetic counterpart, a kilonova, visible in gamma rays, X-rays, optical light, and infrared. It was the dawn of multi-messenger astronomy, and it changed everything we thought we knew about element formation. A kilonova is the explosive aftermath of a neutron star merger. Unlike a supernova, which forms from a single massive star, a kilonova results from two already dead stars, dense neutron stars. spiraling inward and colliding. The conditions at the moment of impact are ideal for extreme Are process nucleosynthesis. Enormous neutron flux, high energy densities ejecta moving at relativistic speeds, dense neutron-rich matter ejected into space. And GW170817 observations from Hubble, Chandra, ESO's VLT, and ALMA revealed light signatures that match the presence of heavy elements like strontium Sr. Lanthanides. Gold platinum researchers estimated that GW170817 produced around 10 Earth masses of gold and several times that of platinum. A 2017 study led by Ido Berger, Harvard, and published in the Astrophysical Journal Letters concluded that neutron star mergers like GW170817 could be responsible for up to 90% of the Are process elements in the universe. That includes the gold in your jewelry, the uranium in nuclear fuel, and the rare elements in your smartphone. As Berger put it, this is how the universe makes gold. The kilonova S light curve, how its brightness changed over time, matched theoretical predictions made decades earlier by astrophysicist Bohdan Paczynski and Brian Metzger in 2010. Metzger and colleagues had published simulations showing that Are process material from neutron star mergers would produce distinctive infrared signatures due to the opacity of lanthanides and actinides. The 2017 kilonova followed that exact pattern. This was one of the most direct pieces of evidence linking neutron star mergers to heavy element synthesis, closing a gap that supernova models had struggled to explain. Compared to quark-collapsed supernovae, neutron star mergers provide longer neutron exposure times, have higher neutron densities, eject cleaner samples of heavy Are process elements. They're also rarer, but more efficient at creating heavy elements per event. This makes them crucial contributors to the galactic chemical inventory, especially for elements heavier than bismuth. The slow path and cosmic collisions. Not all heavy elements are born in violent explosions. An asymptotic giant branch AGB stars are large, aging red giants. A more measured process unfolds, the slow neutron capture process, or S process. This occurs over thousands of years, where nuclei absorb neutrons one at a time, with enough time to undergo beta decay between captures. This creates strontium Sr, barium Ba-Li Pb zirconium Zr. The S process was mathematically formalized by Margaret Burbage, Jeffrey Burbage, William Fowler, and Fred Hoyle in their seminal 1957 paper Synthesis of the Elements in Stars, often referred to as BEFH. This process complements the Are process by filling in isotopes on the other side of the neutron-rich valley of stability. How do we explain the presence of light but rare elements like lithium Li, beryllium B, and boron B? These elements are not efficiently produced in stars. In fact, they're usually destroyed. Instead, they're created through cosmic ray spallation, high-energy protons and atomic nuclei. Cosmic rays collide with atoms in interstellar gas. These collisions break apart heavier elements, forming lighter ones. This process was modeled in the 1970s by researchers such as Ramity and Reeves, and confirmed through isotope measurements in cosmic ray samples, though not a major source of mass spallation. Explains why Li, B, and B exist in trace amounts in the universe. To complete the picture, astrophysicists have identified several other nucleosynthesis pathways. P process, proton capture process, forms rare, proton-rich isotopes of elements like molybdenum and ruthenium, thought to occur in the outer layers of supernovae. New process, neutrino-induced reactions, occurs during supernovae, where high-energy neutrinos interact with nuclei, producing isotopes like fluorine and boron. These mechanisms may contribute only a small percentage of the total elemental abundance, but they help explain anomalies observed in the solar system's isotopic ratios. Each process, from the Big Bang to the death throes of stars and neutron star mergers, plays a distinct role. BBN gives hydrogen, helium. Lithium stellar fusion gives carbon to iron. Supernovae and mergers gives heavy Are process elements AGB stars. gives S process isotopes cosmic rays gives Li, B together. They weave the rich chemical tapestry of the periodic table. As the late astrophysicist Donald Clayton once said, the stars are the crucibles in which the elements are cooked, each with their own recipe. Stardust recycled when stars reach the end of their lives. Whether in quiet fading as white dwarfs or explosive supernovae, they don't vanish into nothing. Instead, they return their enriched guts to the universe. This ejected material forms nebulae, colorful clouds of gas and dust rich in heavy elements like carbon, oxygen, and iron. The Crab Nebula, for example, is the remnant of a supernova witnessed in 1054 AD. It contains carbon, calcium, and iron now drifting through space, ready to be used again. Over millions of years, gravity pulls this gas and dust into new star-forming regions, known as stellar nurseries. Within these clouds, new stars form, surrounded by protoplanetary disks. Planets take shape from accreted metals and silicates. Some of this material ends up in you, in your blood iron, your bones calcium, and even your brain phosphorus. This recycling process has occurred again and again over billions of years. Every new generation of stars inherits more metals from the last, which is why astronomers refer to metal-rich stars as population I, like our Sun. Our solar system formed about 4.6 billion years ago, from a molecular cloud seeded with the ashes of older stars. Meteorites in our solar system carry isotopic fingerprints from multiple nucleosynthesis events, including short-lived radionuclides like aluminum-26 from nearby supernovae, heavy elements like uranium from neutron star mergers. These clues help reconstruct the ancestry of the matter that built Earth and gave rise to life. This isn't poetic metaphor. It's scientific fact. You are made of atoms forged in stars, oxygen from helium fusion, carbon from the triple alpha, processed calcium from late stellar burning, iron from supernovae, gold and platinum from neutron star mergers. Every breath you take is a direct inheritance from ancient stellar furnaces. As astronomer Michelle Thaler says, the iron in your blood came from the core of a star that died billions of years ago. That's not poetic, it's physics. Mapping the periodic table to the cosmos. The periodic table isn't just a chemistry tool. It has a map of the universe's nuclear history. Every element you see on it was forged through specific astrophysical processes. Hydrogen and helium gives Big Bang carbon, oxygen. Iron gives stellar fusion, gold. Platinum, uranium gives supernovae and neutron star mergers. Lithium, beryllium, boron gives cosmic ray collisions. Modern visualizations, such as those created by NASA, CERN, and GINA Joint Institute for Nuclear Astrophysics, color code each element by its astrophysical origin. These visual periodic tables reveal at a glance how diverse and complex the universe as chemistry truly is. Let's break it down further. Element origin: hydrogen, H Big Bang, helium He Big Bang, and stars carbon C triple alpha process and stars oxygen O. Stellar fusion and massive stars iron phase supernova core collapse gold O. Uranium U neutron star mergers, and supernovae beryllium B. Boron B cosmic ray spallation lead PB. Barium bias process and red giants. Each element carries a story, a moment in cosmic time, where extreme conditions enable the nucleus to form and survive. You could build a periodic table of U. Oxygen 65% from red giant stars. Carbon 18%, born in triple alpha reactions. Hydrogen 10%, primordial, from the Big Bang. Calcium, phosphorus, forged in late stellar phases. Iron, blood, supernovae product. Trace gold, brain, nerves, from neutron star collisions. This isn't an abstract exercise. It has a literal history of how matter traveled across space and time to become you. You are the universe, made conscious over the last 13.8 billion years. The universe has performed the most complex chemical experiment imaginable. In its first moments, it gave us hydrogen and helium. Then came the stars, cooking carbon, oxygen, and nitrogen. Supernovae and neutron stars added gold, uranium, and all the exotic heavy elements From chaos and heat came structure. From quantum reactions came life. Every atom in your body has traveled across space and time, through stars that lived and died long before Earth even formed. The story of nucleosynthesis is not just a story of physics. It has the story of how the universe assembled the ingredients for life. As astrophysicist Neil deGrasse Tyson put it, we are not figuratively, but literally stardust. We are chemically connected to all that surrounds us, biologically to all life on Earth, and atomically to all matter in the cosmos. When you look up at the stars, you are seeing your origins. So what about the first stars? The elusive population 3 stars that kick-started this alchemical chain reaction. What were they made of? How big were they? And why haven't we seen them yet? In the next video, we'll explore the search for the very first stars, the silent architects of the periodic table, and the key to understanding the early universe. If this journey into the universe's chemical origins moved you, share it, like the video, subscribe for more stories from space. Comment which element's origin surprised you the most. Thank you for watching, and until next time, remember, you are the universe made conscious. Stay curious.